Okay, welcome to another Stat 510 video. The title on the previous slide was Parametric Inference 1 because I decided to split up that chapter of the book into two. In this video and this week, if you're following along in the course, we're going to talk about constructing estimators, and then next week in the follow-up, we're going to talk about properties of those things. But so this week, the homework is going to be more focused on mechanics, and next homework is going to be more focused on sort of the properties of those things that you're mechanically deriving. Okay, so let's get into it. So kind of a lot of stuff we need to talk about in this video, and this is roughly it. We're going to sort of restate what a parametric model is, and then sort of do something in the opposite order of the book, which is immediately talk about checking assumptions, because when we're doing parametric inference, one of the things we're doing is making assumptions. Then we're going to talk about method of moments, maximum likelihood, and make a quick note about the parametric bootstrap. Okay, so these next few slides, I guess is what we call them, are going to be a bit of a recap from what we saw before, but now because we're actually going to do these things, we need to talk about it again. So remember that our goal in inference was to say, okay, we have some data that we assumed came from some distribution f. How do we infer f? Or in other words, how do we learn f? And that's what we've been working on so far, but in this video, we're going to do it a slightly different way. So, and again, remember that procedure looks something like this. So we say that this distribution, or the sort of state of the world, we can sample from it to obtain some data, and then with that data, we apply some function to it, which we call a statistic, that hopefully will tell us something useful about the distribution from which that data came from. And one of the key tasks that we are doing is just trying to directly infer the distribution function. Okay, which is exactly what I want to talk about here. So that's what I just said. The idea is, okay, so we believe we sampled data from some distribution. Let's try to figure out what that distribution was. And up to this point, we've tried to do that non-parametrically. And so basically what we did was we directly estimated that distribution with the empirical distribution. But now we're going to move into parametric estimation. And then the two main methods we're going to see today are method of moments and maximum likelihood. Okay. So this is sort of the slide that where we talked about what a parametric model is. But basically, we assume that the distribution lives in some family of densities that are parameterized by some parameter theta. And so for a different theta, that gives us a different density, therefore a different distribution. But we can sort of summarize the whole distribution by this theta, which is its parameters. So we've reduced the learning task down to learning the parameter, then learning the whole distribution at once, non-parametrically. So for a quick example here is a really long-winded way of saying that, like, we're assuming a Bernoulli model. And so hopefully at this point, I'm just going to move myself real quick. At this point, this x1, x2, xn from Bernoulli P notation is familiar to you. Essentially what we're saying is we believe that this random sample came from a Bernoulli distribution with parameter P, and then our only job is to learn P, because we already assumed the distribution that the data came from. Another recap slide real quick. So here we're assuming a normal model for the data, and that's a two-parameter model. You have mu and you have sigma. So in blue here, x1 through xn, we're assuming is normal with mu and sigma, or sigma squared, doesn't really matter. But our goal then is to learn mu and sigma. Sometimes we care more about one than the other. Like, say we care about mu ultimately, but we still need to estimate sigma. In that case, sigma would be called a nuisance parameter. Okay. So in this video, I mean, there's a lot more to inference than just point estimation, which we've seen through from making confidence intervals, and later on we're going to do tests. But in this video, we're going to focus on point estimation. So that is, we want to find some theta hat that is a function of the data, which is a best guess for theta, which is some parameter that we're interested in, which is some fixed but unknown quantity. So that's our task today. We want to apply some function to the data that makes a reasonable estimator. And again, remember that those estimators, before you plug in actual data points to them, those are statistics. Once you plug in actual values from data you actually have, then it's an estimate. So estimators create estimates. I realized I didn't make a slide about that, but I'll do that at the end maybe. Okay. And then, so because of these things are random variables, they also have a sampling distribution. That's what we're going to talk about next week. Okay. So right off the bat, I want to talk about this notion of assumptions, because that is the biggest difference between what we're doing now and what we did previously. When we were using the empirical distribution, we weren't really making any assumptions. But now, in this statement here, what I'm doing is that this part of the statement here is a bunch of assumptions. So technically, we're assuming a bunch of things here. For one, we're assuming our data is IID. And then for the D part of that, the distribution part, we're assuming it's a normal distribution with mean mu and variance sigma squared. We're assuming that we need to learn mu and sigma from the data, but we are assuming that some normal distribution was what gave rise to this data that we are going to potentially sample. So this is essentially a way this estimation could go wrong, because if you assume just a wildly incorrect model, that'll cause a bunch of problems. So the question is, well, how do you check these assumptions? So in this very simple case, there are some things we can do. So one of the ways to check it is graphically. Oh no. Oh gosh. I have my settings all messed up. Let's try that again. Graphically. So plot a histogram, right? Plot a histogram of the data. Will this prove that it's normal? No. But if it's bimodal in the histogram, you could reasonably assume that that's not normal data. If it's massively skewed, you should question whether or not that's normal data. And then we can also derive formal tests. So perhaps you've heard of things like goodness of fit tests previously. And when we get to hypothesis testing, we'll see some of these things. But know that for the rest of this video, this is something that's going to be looming in the background, but we're not actually going to do, because we're going to talk about the methods of actually driving the estimators, not so much addressing whether or not the model is appropriate. But that should be at sort of the forefront of any real data analysis you're doing, because if you're assuming a model, hopefully it's not a terrible model. Okay. So our first method for estimating parameters for parametric inference is method of moments. Before we actually talk about method of moments, we need to quickly talk about moments. So what we have here is some parameter theta. And we're going to say that it could have k components, theta 1, theta 2 through theta k. And then, sorry, I was going to move myself around a little bit. So then we need to talk about moments and sample moments. So the first thing we have here, I would call, well, actually, in particular, the way I wrote it, it is the jth moment. You might call this the jth population moment, because these are functions of the parameters, the true parameters and through the distribution that those parameters specify. So, for example, the first moment would just be the mean. Right. So, but importantly, sorry, I have some notes to myself here. Oh, right. So, this here is the distribution that is generating the data, which is a function of the parameter that we care about. So what did I say here? Distribution is function of the parameter. And sort of therefore, the moments are also functions of the parameters. Okay, but remember, this has nothing to do with data. We're sort of talking about things that have to do with the probability side of our circular diagram there. Okay, but now we're going to move to the other side of that diagram and talk about moments of the sample. So what I have written here is the jth sample moment. So importantly, sample. So we got two moments uh, that we have to deal with: the population moments, or just moments, and then the sample moments. So moments are functions of the parameters or the distribution that is on the left-hand side of. Sorry, I'm referring to this picture. So moments are on the left-hand side. Oh, is my camera reversed? This is maybe confusing. But anyway, moments are here. Sample moments are here, right? So that's what we have here. And when we actually calculate the moments, which we'll do an example of in a second, often, again, so in a parametric model, we're assuming a distribution up to but not including the parameters. So the end calculation here won't be a number or something. It'll be literally a function of the parameters. And we'll see that in a second. Okay, so what is method of moments? Let's say you have some theta with k components you need to estimate. Well, find k moments, calculate the k sample moments, equate those two things, solve for the parameters. That's effectively what method of moments does. So again, this is the second moment. And this here is the sample second moment. Or let's call it the second sample. And we've equated those two things. So the thing on the right-hand side is a function of the data. The thing on the left-hand side is a function of the parameters. So through doing this, we're going to have k equations. And we're also going to have k unknowns. That is horrible handwriting. And then you solve that. And this hopefully is a somewhat intuitive procedure, right? We would hope that the sample moments are close to the real moments. Okay, so quick example. Actually, two quick examples to show how to do this. So in this example, we're going to assume that x1 through xn are IID geometric random variables. And so what we would do first is say, well, I want to find, so we have one parameter, so we need one equation of moments. So first I'm going to find the first moment, which is the expected value of x to the 1, otherwise known as the expected value of x. And then I would just go to the back of the book and look up what that is, because this is a well-known distribution. It turns out it's 1 over p. If you were dealing with a lesser known distribution, hopefully you can still look it up, but maybe you have to do a little calculus. But, at the end of the day, we know how to find expectations. Okay, and then the first sample moment is just by definition something like this, which we often simply notate as x bar, maybe x bar sub n. All right, well, then what do we do? So we want to equate this with this. So I say 1 over p is equal to x bar. And then, so the p there is the method of moments estimator. I just need to solve. So I get p hat is 1 over x bar. And this is the method of moments estimator. Okay, cool. So remember, at this point, the way I've written things is maybe a little bit ambiguous, but I would call that a big X bar because I'm doing this for a potential sample. And so I'm calling this an estimator, O-R at the end, estimator. Let's say that we actually got some data that was like 2, 3, 3, 4, something like that, right? So this data has an X bar of 3. So for this particular data set, we would have p hat is 1 over 3, right? So this is an estimate. So an estimate is something for a particular data set. An estimator tells you, hey, with some data, what is the procedure I need to do to spit out a numeric answer? It's a minor point, but I think it's important that you keep those two things separate. An estimator can be viewed as a statistic. An estimate is a value of a statistic when it's applied to a particular data set. Okay, cool. All right. Another quick example. So this time, let's assume we have some random sample that we're going to assume came from a normal distribution with some unknown mean and unknown variance. So the first thing I need to do is find the first and second moments, which I've done here already. Notice that they're both functions of the two unknown parameters. So what I need to do then is set those things equal to the first and second sample moments. So let's take the first moment and set it equal to the first sample moment, like that. Then let's take the second moment and set it equal to the second sample moment. I'm now going to put hats on these because the values of mu and sigma that satisfy this set of equations are the method of moments estimators. That's not a great arrow. I don't like the way my arrows look. Anyway, so doing a little bit of algebra, but fundamentally we're solving for mu, we're solving for sigma or sigma squared, however you want to view it. We end up with mu hat is x bar, and sigma squared hat is something like this. Okay. So that's using method of moments with two parameters. Honestly, the hardest part is the algebra that I didn't do here, but that's not statistics, that's algebra, so we're not too worried about that. Okay, so now we want to start working towards talking about maximum likelihood, which is the more interesting thing. So first, I want to talk about likelihood. So we're going to consider, well, not even likelihood yet. So maybe the word likelihood shouldn't appear on this page, but it does for now. So let's say we know the distribution is a standard normal, 0, 1. I think I don't need to explain that sampling and getting a data point here is less likely than sampling and getting a data point here, which is less likely than sampling and getting a data point here. So basically, regions of higher density, we think it's more likely that data that we sample will, show up in those regions. So as we go from here to here, those observations are, let's say, more Okay. I think that's pretty intuitive. Oh, the thing I want to say is in this example, we're saying this is known. So right now we're saying I know a distribution. How likely is it that I see a particular observation, right? So we're not doing likelihood right now. We're just kind of doing like density calculations, right? Because at this point the density is here. At this point the density is here. At this point the density is here. But we understand that if we sample from this distribution, we're more likely to get points in high density regions. Okay, cool. All right. Now let's consider multiple data points at once, right? So basically, I'm saying if I know that I'm sampling from a standard normal, how likely is I see a possible random sample of data, right? So in the far left, I think if I told you that we were sampling from a standard normal, you would say, well, yes, I could see this data, but it doesn't feel very likely. Now, if we move one to the right, well, this seems a little bit more likely because now we've seen some observations below zero, some observations above zero, except they seem a little bit too spread out, like they're occurring almost uniformly in that area. And then all the way on the right, well, now we have more points in the higher density regions, but we still have some points in the lower density regions. This seems like the most likely sample of these things. So similarly, again, if we assume we know, or not even assume, if we know the distribution is standard normal, we would say that moving from left to right, that rightmost sample is just more likely. So what did I say? More likely to be sampled. Okay. Now we want to flip this. Now let's say I'm going to assume that my data were sampled from a normal distribution with an unknown mean but what we're just going to say a standard deviation of 1 just to make my life easier for what I'm about to draw, right? So now what I have plotted here is I obtained this data that we see here. So now I have data. So now what I'm going to try to do, please bear with my artistic skills here. So I could say, well, that data could it have come from this distribution? So a distribution with that mean and variance 1 that looks like that. Well, yes, but given the logic that we established here, it would be very unlikely. Similarly, if I said, well, what about something like this? So what if I asked the question, hey, could this data have come from this distribution? Yes. Is it likely? No. I should say that these two distributions should have the same exact shape. I'm trying to just only shift them because they all have the same variance. What if I asked, could the data have come from this distribution? Yes. Does this seem like likely data to have come from this distribution? Very much yes. So basically, if probability is going from knowing a distribution, saying like what's the probability of observing, say, a point, that occurs greater than 5 or whatever, that's probability. Likelihood is the opposite. Given the data, well, which distribution makes it so that data is most likely to have come from it? So in this example here, basically what we're doing is we're saying, okay, so we're constrained to normals with variance 1, so we can shift that normal to be anywhere on the real line we want, but we want to put it somewhere that makes it look like that data really came from it. And if we were to allow the variance to be unknown as well, then we'd also be able to modify this. So we'd not only find where it should be, but what it should be shaped like to best match the data. So that is the idea of maximum likelihood. So now let's formalize it a little bit. So to do so, we first have to talk about the likelihood. So let's say we have x1 through xn that are IID with some PDF f of x. And now I'm writing the PDFs to note very strongly that they're a function of either the data or theta. And I would note that we don't actually need IID observations. It just makes our life easier. And I'll note where that comes in a second. So the likelihood, with which I denote with the fancy script L, is a function of theta, right? And so what it is in terms of like the symbols that we write down, it's the joint density of the data. But we can only evaluate it as a density if we knew theta and then plugged in the x values. But that's not what we're doing. We're doing the exact opposite of that. We are assuming that the data are observed. So we're going to have all the x values already. It's theta that can vary and that we're trying to find. So this likelihood assumes data is observed, and it is a function of theta. And so if we assume that things are IID, well, then that joint distribution becomes the product of the individual densities for each observation, which is a really nice thing. It makes life a lot easier. Okay, so to really drive this point home, the likelihood is a function that takes in as input some value theta and spits out a number that's between 0 and infinity. And I should note that it does not need to integrate to 1. Because even though the symbols are that of a density, it's not a density. It is a likelihood, so it does not need to integrate to 1. I should say we're talking about densities here, but this also applies for mass functions. But yeah, so they're not probabilities, so we don't need things to integrate or sum up to 1. Okay. And then also there's this notion of the log likelihood, which is simply taking the log of the likelihood. I've left a notation here. I will often painstakingly write out log and then likelihood just to really drive the point home. Because every semester someone comes back and asks this. Yes, it's natural log. I frankly don't know any other log. When I see log, I think natural logs. So do statisticians. So when we say log, we mean natural log. Don't hit the wrong button on your calculator at some point. Anyway. Okay, so what do I have here? So this picture is maybe not great. So the idea here is that in both pictures, it's the same data. And maybe it's not super clear. I'm kind of regretting this picture. The models are just shifted a little bit. So in the left-hand side, I already did this, but so at each data point, I put a dot along the density curve. So what the likelihood of that data would be, it would just be those values of the densities all multiplied together. Whereas over here, those values would be like here, here. I don't know why I didn't just leave this on here. There's no benefit to drawing this. I feel like I'm going to mess it up too, but hopefully you get the picture, pun intended. So there are the values of the densities at each of the observed values here. And if I multiplied those together, that would be the likelihood. And hopefully it's clear without actually doing this calculation that the likelihood on the left is going to be higher than on the right. So I was just trying to try tie this slide to this slide was the idea here. So hopefully that helps. Okay, so the maximum likelihood estimator, which we often call the MLE, is the value of theta that maximizes the likelihood. Statisticians are great at naming things. So again, I should note that I assume that everyone in this class has already seen likelihood, and we're just sort of recapping right now. But if you haven't, here you go. But so something that you guys are already all thinking would be that the value of theta that maximizes the likelihood is the same as the value of theta that maximizes the log likelihood. So oftentimes we will simply maximize the log likelihood just because it's easier to do. But sometimes you can directly maximize the likelihood. Okay, so let's do a few examples. They will go from boring to less boring to actually interesting, in my opinion. This one's boring. So here we're assuming that x1 through xn are sampled from a geometric distribution with some parameter p. And here I've written down the density, a mass function for a geometric random variable. So the likelihood is a function of p. I often drop the subscript n. I think it's clear from context. So it is the product of those individual densities because we're dealing with IID data. And just doing a little bit of mathematic rearrangement here, or algebraic rearrangement, we get something like this. Something like that, I think. All right. Just going to move that over just a little bit. Okay. So then I want to take a log. Well, so again, my goal is to maximize this. I just think it's going to be easier if I take a log. So I'll take a... Oh gosh, I'm not writing very well. Okay, so this should be n log p plus sum of the xi minus n times log of 1 minus p. Okay, great. Cool. So now I want to maximize this function, which, amounts to taking a derivative, setting equal to 0, solving, and then, maybe taking another derivative and verifying a few things. I'm only going to do part of that process, but we're just all we're doing is like at this point I should claim victory and be like, well, statistics is done, math is happening, but just for the sake of completion, I'll take a derivative with respect to the parameter, which I believe is something like n over p. There's gonna be a chain rule minus here, and then sum of the xi minus n over 1 minus p. Something like that. So if I set it equal to 0 and then solve, I'll end up with an MLE of 1 over x bar. Technically, we need to do a few other things to verify that that's a maximum, but we're going to ignore that for now. And I guess this is kind of boring because I'm realizing that we've seen this exact answer before. It's not always the case that maximum likelihood gives the same result as method of moments. Okay. Okay, so slightly less boring, but still boring. So now we have a two-parameter model. So now we're assuming that the random sample is from a normal distribution with some mean mu, some variance sigma squared, and I have already written down the likelihood. But so now I'm not going to do this whole problem. We have two parameters. So now we're going to have to, come up with some system of equations. So supposing that I had the log likelihood, which is the log of what you see here, I would take a derivative with respect to mu of the log likelihood. I think we're writing the likelihood as a function of sigma, that doesn't really matter. And set that equal to 0, along with taking a derivative with respect to sigma. Setting that equal to 0, and then, doing some stuff, but ultimately solving the system of equations. So solve for mu comma sigma, and that would get you the MLE. I'm not going to do that because it's just a bunch of algebra. I will certainly not do it right. And the resulting estimators are not interesting. Okay, let's do an actual interesting example. So my opinion on how to do this problem is just to intuit the answer. So here we have x1 through xn, uniform 0 theta. So I've written out the density there. So I think intuitively most folks would guess the answer here, which is that the maximum likelihood is just going to be the maximum of the data. Let's go through this carefully. So it turns out that the likelihood here is going to be something like this. Let's see, theta. Okay, so this x sub n, that is the maximum of the data. Or the largest order statistic, if you will. Which, remember, when we're actually calculating the likelihood, that is a known value. So again, this is a function of theta, right? So we have to remember that. So after we cross theta equal to xn, well, then the likelihood just decreases. So the likelihood is 0. Then it shoots up to some value when we hit theta equal to the maximum. And then as we make theta bigger, the likelihood goes down just via what this function looks like here, right? So the bigger theta is, the smaller that function is. So theta hat, the MLE, is just the maximum of the data. Okay, but I would not fault you if you were staring at your screen right now and saying, well, what? I think that's a little confusing. So let's try to break that down a little bit. So let's give some intuition for this. So here I have some data that, we're going to, find the maximum likelihood estimator for. So let's first try to posit a guess of theta being right here. I'm going to call it theta 1. So that's saying that a uniform density would look something like this. But that's kind of a problem because for the 3 data points that are to the right of theta, the density is 0. Therefore, the likelihood is 0. So for that value of theta, the likelihood of theta 1 is 0. So that's probably not going to be a good choice. So now let's do, and this is not to scale. I'm sure the heights of my densities are not going to be correct, but they'll be rank ordered appropriately. Let's say we try to theta out here. So let's call this theta 2. So because I'm covering more space on the x-axis, which I should maybe label actually. So this is x, this is f of x comma theta, I guess, or colon, semicolon. So here, because it has to integrate to 1 and all that good stuff, it's going to look something more like this. And now, at each point, the density is non-zero. So we obtain some likelihood that's not 0. So definitely the likelihood of theta 2 is bigger than the likelihood of theta 1. Okay, great. Well, what if I make theta right here? And don't forget there's a point there. So again, this is not quite to scale, but I think the density would then look something like this. And so all of these points now have non-zero density, but they're all bigger than that other one. So what that means is that the likelihood of theta 3 is bigger than the likelihood of theta 2, which is definitely bigger than the likelihood of theta 1, which is equal to 0. So hopefully you can see that theta 3 here is the MLE, and any theta to the left of it, which is lesser, will have a likelihood of 0, so we don't need to consider it. And anything to the right of theta 3 will have a lesser likelihood. So I guess I should probably maybe draw one quick picture. So here is okay. So now that is the data view, I guess I would call it. Now let's plot the actual likelihood, right? So this axis is now theta, and this axis is L of theta. So the likelihood is going to look something like this. It's 0. Oh, and this is the point x sub n. So it's going to be 0, it's going to be 0, it's going to be 0. Then suddenly it's some positive value. And then according to this likelihood function here, it decreases something like that. So this is the MLE right here. Hopefully that breaks that down a bit. But I think the intuition behind, if you want to estimate the endpoint of a uniform, use the maximum. Okay. So a couple more quick things. MLE is equivariant. What we mean by that is if theta hat is MLE for theta, well then G of theta hat is MLE for G of theta. Pretty nice idea. So quick example. So here we have x1 through xn, assume it to be from a normal with mean, mu, and variance 1. Therefore, the MLE for theta is x bar. Therefore, e to the theta hat, which is e to the x bar, is MLE for e to the theta. Very, very useful idea. Okay. Quick note about optimization here. So ultimately, when we're doing maximum likelihood, we're maximizing a likelihood. More specifically, often we're trying to solve this equation here, say in the univariate setting, or perhaps a system of equations. And this system of equations might not have an analytic solution. Not have solution. So often in practice, to maximize something, you're going to have to use a numerical optimization routine. So in the homework, you're going to encounter 2 of these. One is Newton-Raphson. I can't write. Which is a pretty simple root solving idea. And then in the challenge problem this week, you're going to look at the EM algorithm, which you'll use to fit a mixture model, should you choose to accept the challenge question. Okay, so just a note there. Okay, sort of wrapping up and introducing one last idea. So we've been so far mostly focusing on this idea of, okay, well, we assumed some distribution and we need to learn its parameters. But that was all in service of learning this distribution on some higher level than thinking about point estimation. So, like in this example here, well, so if we have this random sample and we assume that it's from some normal with mean mu, variance sigma squared, and I, find these MLEs, and like let's say that I actually like plugged data into them, and I don't know, for some data set I get a mean of like 3.1 and a variance of like 2.1. I said 3.1 I think, but I wrote 3.5. Well, so if I plug those into here, well then that's a learned distribution. Okay, cool. So in the same way that when we did the empirical distribution, that gave us a direct estimate for the distribution that the data came from, same idea here. We get the point estimates for the parameters, we plug them into the distribution we assumed. Okay, well now that distribution is an estimate of the distribution that we think the data came from. So that's useful because we could talk about the parametric bootstrap real fast. So previously, when we did the bootstrap, we did a non-parametric bootstrap. So we didn't make any distributional assumptions. So basically what we said was, okay, use the empirical distribution here. So use the empirical distribution as an estimate of the actual distribution, and then sample from the empirical distribution to generate bootstrap resamples, and then calculate your statistic on that, and then you have bootstrap replicates and you're off to the races. Okay, great. Well, there's another way to do the bootstrap. It's called the parametric bootstrap. So here we're going to assume some parametric form of f, and so I've indexed it by theta here. And then we're going to estimate those parameters theta. And then once we have estimates for them, theta hat, we'll plug them into f, and then you can sample from that learned distribution, a data set of the same size. So what I'm saying is, to get a bootstrap resample, sample from the normal distribution in the previous example, like mu hat sigma squared hat. So basically, instead of generating bootstrap resamples from the empirical distribution, you generate the bootstrap resamples from the distribution that you learned parametrically by plugging in the point estimates for the parameters to that distribution. So this idea will be useful for estimating standard errors of maximum likelihood estimates. I think you'll try this idea once on this homework, but next week when we talk about standard errors of these estimates in general, this will be an idea that we compare against other ideas. We'll talk about some theory behind the MLE in terms of its sampling distribution, so we'll need to talk about its standard error and all those things. But for now, I just wanted to highlight this idea that we're learning a distribution, and in the same way where we can take the learned distribution and generate bootstrap resamples with the empirical distribution, we can actually do the same thing here. Okay, so I assume pretty much everything I said in this video is not all that new to anyone in Stat 510, but I'm hoping that the homework really jogs your memory, but also sort of pushes you towards some of these new ideas. I really like the homework for this week. Well, that is, I liked the homework for this week after I cut it in half and added some problems instead of doing all of the parametric inference chapter this week. Okay. That's it, right? Yeah. Okay. So, as always, if you made it to the end of the video, good job, and I'll see you in the next one.